Hello, I'm Emmanuel Markoulakis from the Hellenic Mediterranean University here in Chania, Crete, Department of Electronics Engineering. I will present to you today my unpublished, most recent material, research material, which is, I believe, something which you find interesting. So the title here is the deterministic control of the spin of the electrons, of the quantum spin of the electrons. As you may know, is that the problem of the quantum entanglement communication is that the non-communication theorem applies, which means that of course you have quantum entanglement instantaneous action, which is instantaneous. There is no speed limit in the propagation of information, but because you cannot transmit any useful information using quantum entanglement, spin entanglement, then also Einstein is not violated, and because there is no actually transfer of any information. Yes, and the problem is that we cannot control the quantum spin of the electron. If we put an electron, a free electron, inside an external magnetic field, an homogeneous field, which means same density, straight flux lines, then we cannot control if the electron, its intrinsic magnetic dipole moment, will end up aligned with the external field, facing the same direction, or its intrinsic magnetic moment be antiparallel. So it can be either parallel, which means complete alignment with the vector of the external magnetic field, or in the opposite 180 degrees direction, which is antiparallel alignment. And this is random. We cannot control this. So therefore, we cannot assign any digital binary bit information to it. We cannot decide because we cannot control the spin. We cannot say, for example, if it's spin up the electron, then we assign bit 1, logic bit 1. Or if it's spin down, we will assign antiparallel to the external magnetic field. Then we will assign, for example, bit 0, logic bit. So because there is no control of what information we can transfer using quantum entanglement, there is no use of it. That's the no communication theory. But what if we could control to a large percent, maybe 80% or even 100%, this random quantum spin of the electron? Then we could assign logic bit 1 and 0, and then yes, we can have instantaneous quantum entanglement communication between two entanglement systems. Alice and Bob. Yes. So this is my research the last few months. But of course, I have a big background of related research, which this is just an application of my more fundamental research about the intrinsic mechanics of the electron. So let's go now directly to the slides presentation. Yes. Yeah. So just give me please a moment. Okay. All right. Yes. So let's start the presentation now. So here is a picture, a snapshot I borrowed fair use from the recently presentation of the Fermilab G minus muon experiment of the anomalous magnetic moment of the muon. And this just a recap of what the theory says. So we have the spin of the electron, which has a magnetic moment, which is symbolized with this arrow here. And then we have an external field, which is symbolized the magnetic field direction with this green arrow. And when we put a free electron inside this kind of homogeneous external magnetic field B, it starts processing its magnetic moment around the vectors of the external field. This frequency of precession is or electromagnetic precession. It's calculated with this equation, where omega is the precession frequency, the angular velocity in rads per second. And here we have the G factor, which is a very important factor and constant in quantum mechanics. This is the charge of the electron, the mass, the speed of light, and the strength of the external magnetic field. So, for example, we see here that the precession frequency it's dependent from the strength of the external magnetic field, and this calculates to approximately for 1 Tesla magnetic field external, we get about 28 gigahertz of precession frequency. Yes, this is in rad per second, but if we convert it to hertz in the SI units, this frequency for one Tesla B field, external field, the electron processes 28 billion times per second. Yeah, and this is the quantum interpretation of the precession. But of course, quantum says that this precession is the spin of the electron is a quantum device, quantum characteristic, and this is happening without any spin. So there is no quantum mechanics says there is not actually no any spin. The electron does not spin physically, but it has still this kind of angular momentum and magnetic spin we measure. Of course, my theory now, which is a semi-classical theory, says no, the electron is not it's not a dimensionless point. It has the charge of the electron has a specific finite radius, and at rest, of course, all this. And my model is for the electron, for the free electron at rest without any translational motion. And the exclusive goal of my theory is to understand better the intrinsic mechanics of the electron properties, its charge, from where its charge originates, its helicity, its intrinsic magnetic dipole moment, its angular momentum, and so on. So we do, in my theory, we have the electron has it's actually also spinning around its magnetic moment, its intrinsic magnetic moment, and we can see that here in this animation. So this is the quantum spin, including precession, the semi-classical interpretation of the spin of the electron. Here we see a spin-up electron, and we see that the whole electron spins around its magnetic moment axis, which is this red line here, in a sense anti-clockwise, but the precession is in the opposite direction, is clockwise. So the electron spins anti-clockwise, but it processes clockwise. And this is for a spin-up electron. We have the other here. So this is always a bird's eye view from above the poles of the electron, the north and south magnetic pole of the electron. And here we have the opposite directions of spin. We have actually the electron spinning physically in the clockwise direction, but the precession is always in the opposite direction, which is in this case anti-clockwise. So it's similar to mass precession. We have the relativistic to mass precession. And how we see it in an electron, we can see its spin axis, its spin vector, by using our right hand, always a right hand rule, a curve from we curve our fingers to the direction of the spin, of the physical spin. So if we curve, in this case, the direction to the spin, which is here, this spin here, we see that our thumb will point, our thumb will point down. So the spin vector is, the spin vector here is spin down. So this is a spin down electron. Yeah, so we go now, we leave this and continue here the presentation. So, but what is not very much known is that there's a precession angle here, which is fixed and independent from the magnetic field. So the more we strengthen up the magnetic field, it will precess faster and faster. But always this angle here is fixed, and this angle is called magic angle, not to be confused with the graphene research. We have also there a magic angle, but this is a different magic angle. This actually is a mathematically defined term. It's arctan of square 2. We'll see that later on. You can Google it. Google it. It's a mathematical term angle, and you can Google it in Wikipedia. So this angle remains always the same. And here's the mathematical definition of the magic angle. It's arctan square root of 2. It's approximately 54.7 degrees. More accurately, 54.74 degrees, but it's an irrational number actually. And geometrically, it's defined when you go to the opposite vector here of a cube, to the angle here. This angle to the z-axis is always 54.7 approximately degrees, the magic angle. And this is independent of the size of the cube. So you can have an enormous large cube and a very small cube. This angle will be there always the same, namely approximately 54.7 degrees. And this is referred in mathematics as magic angle, and you can actually Google it in Wikipedia. So yes, this angle now is, and of course it's complementary. This to 3.74, it's complementary to the minus z-axis angle. This is for the plus z-axis, and this is for the minus. This angle is actually responsible for the quantization of the electron spin in space. We see also in the Stern-Gerlach experiment. And this is conventional knowledge. It's nothing new. The only thing my theory says different up to now is that the electron is actually a finite size manifold, energy manifold. It consists not from more elemental particles. No, it's just a flow of energy. It has a finite size and it's physically spinning. This is my theory, the classical theory. So yes, so why is this angle? In order to answer this, why this? Because there must be something intrinsic to the electron which dictates this angle. So my theory says, in order to find the reason, we have first to give you some points for fundamental to my theory, so you can understand where this comes from. So this is not a toy model, but actually the physical manifold, a vacuum flux manifold of the charge of the electron. So you have this kind of manifold. You have this horn tube here connecting the two holes in the two apertures here in the manifold. And this consists, this line here, which is the intrinsic magnetic dipole moment of the electron. And here on the surface, all these lines represent the charge of the electron. So it's actually the charge flux manifold of the electron. So if you ask now what this blue lines represents, this is vacuum flux, because in my theory, there are no elementary particles of the standard model, electron, quarks, and so on. They are all made from this vacuum flux, of this quantum vacuum form flux, which also conventional theory says about exists, and is actually a stream of virtual photons, not to be confused. So each point here of these lines, of this vacuum flux, is a virtual photon. Please don't to be confused virtual photons with normal photons. It has nothing to do with normal photons. These are actually the particles of the vacuum. We know nothing of, we just speculate these particles. Some physicists say they are not even real, but of course they are real, because we can measure the quantum fluctuations. We cannot measure, we can extrapolate the quantum fluctuations of the vacuum. And please, you have also heard the description that constantly we from the vacuum, from nothing, are coming out particles with their antiparticles, like electron and positrons, and at the moment, at the instance they appear out of nothing, they annihilate together and disappear. But this is, please, an effective explanation the physicists are using to justify, to explain why from nothing comes something, and then something goes back to nothing. It's not an actual thing, ontological. But yes, the vacuum flux definitely exists. It's as a coherent stream of, we call them virtual photons. And this, in my theory, is the most elementary kind of energy. So, because all particles of the standard model, which are, they say they are elementary, but not in my theory, are made up of this vacuum flux, this coherent stream of virtual particles we do know nothing of. We cannot see them, we cannot experimentally verify them. They are well known. They are the particles which are responsible for the three of the five of the four forces, three: the electromagnetic, the strong force, and the weak force, which transfer at the quantum scale these forces. And they are called virtual, but we cannot have, we have not seen them, and cannot experimentally verify them, but they must be there. So yes, and now my model says there are two kinds of rotations here involved in this manifold. We have an poloidal revolution here, going along the magnetic moment axis, north-south pole. So imagine like a string. Yes, my theory of the electron is not a point theory of the electron. It's more like a string theory of the charge of the electron. So you have this blue ribbon, and you have this kind of vertical along the z-axis revolution of this ribbon. And at the same time, you have this equatorial now spin. The whole thing, the whole manifold spins around the z-axis, the magnetic moment axis. So this also represents, in my theory, a twisted spin-half photon. A normal photon, geometrically, it's you can interpret it like a ring, a spin one, a circle. But the electron, my theory says, is a twisted, deformed photon, which has now a spin half, not a spin one. And this electron relativistically revolves and spins in superposition in these two directions. And this creates the whole charge electromagnetosphere of the electron, the charge of the electron, which is represented with this animation here. Specifically, very important is the definition of the G factor, which my theory is just says that it's the ratio of frequency, so how fast this equatorial spin is compared to this vertical revolution here. So you have the equatorial rotation, which is symbolized in hertz units, not watt hertz, because my electrical engineer background, I'm using best hertz and not angular velocity rad per second. So this frequency here must be a double of twice the vertical rotation. So the equatorial rotation is twice frequent, twice faster than this rotation here, the vertical rotation. And this is the Dirac G factor. Of course, you have also the anomalous magnetic moment of the electron. Therefore, this G factor is not exactly in practice 2. It's 2.00 something, 23. It's a bit more than 2. But the Dirac G factor is 2. In my theory, uniquely says that this is actually a frequency ratio. You have two Zeta-Bewegung, we can say. So these two rotations, oscillations consist the so-called Zeta-Bewegung of the electron, which also Einstein has referred to, and Dirac and all the greats of quantum mechanics and general relativity. And yes, and this ratio of these two oscillations, the frequency of those, define in my theory the G factor. So it's a way to physically and ontologically explain what this G factor is. And this is also called G factor is also called a 4 pi symmetry rotation. So in order if you assign a point here, a red point, for the electron, in order to return back to the same phase, it has not to do a 2 pi rotation, 30 and 360 degrees, but it must rotate twice. So it has to do a rotation 720 degrees. And this characteristic of the electron is called the 4 pi symmetry. Yes. So going deeper now, we see these animations in my theory. So yes. So again, here we represent these two type of oscillations, rotations, and superposition. You have the Fs revolution along the z-axis, along the magnetic moment axis, and we have in superposition this equatorial now rotation spin, and both combined give the final theta pervading, the final composite oscillation of the electron, which is here in this right-hand animation. You have in the same time revolution of energy of the charge and also equatorial spin. Yes. And if we now see that with a more detailed animation, we see that as now as this is what I call a twisted photon, which revolves, and this is represented here with this yellow trace we can see. At the same time, also the whole twisted photon equatorial spins, and then this gives the final composite rotation oscillation of this twisted photon, which, because it's relativistic spin revolution, gives the final charge of the electron, generates. So it's the dynamo. This is actually the dynamo of the charge of the electron, generates in this specified manifold volume in space, generates the charge of the electron, because this is spinning very fast relativistically. We will see later on. And this generates the charge of the electron. So fundamentally, my theory that says that the charge of the electron is a twisted photon, a twisted spinning, revolving, and rotating photon, which generates the whole charge of the electron. So yes, let's continue now. Presentation. So this is the last slide, which presents the fundamental about the most fundamental points about my theory about the intrinsic mechanics of the electron. So my theory also defines physically the fine structure constant, which is, you have heard about this value, this constant, the universal value of electromagnetism. It's 1 over 1, approximately 1 over 137. But nobody really knows what the physical origin is of this constant, which says it's one of the most important constants in our universe, and without it we could not have any matter and mass, and will not exist at all. Yes, but my theory says that this constant is intrinsic, embedded inside the charge of the electron, and specifically it's a geometric proportionality constant of the manifold geometry of the charge of the electron. So you have here this tube here, imagine like a straw. You know the straw we drink our coffee, iced coffee or what, chocolate or what, whatever. So this has a radius, it's empty side, it's a straw, this tube here, this flux tube, and it has a specific radius. So if you compare the radius of this small radius of the flux tube to the radius of the whole charge here, then this gives a number, the fine structure constant. So it's embedded inside the geometry of the charge of the electron, which in my theory allows this to happen, because my theory gives us a finite size for the electron. It's not what conventionally quantum theory says, that it is a dimensionless point. No, I believe that it has a specific finite size dimensions. always at rest. I'm talking always for the electron. Bear this please in mind. My theory refers only for the electron at rest, free electron at rest, and without it having any translational motion, flying in space without that. Yeah. So now, even after our research, I did this research blindfolded, and then I came up with this novel equation, theoretical. Sorry, it's not my equation. This is in the literature. This is my final equation, and also this here, this pair of equations. But this here is you can find it in the literature, which says that the fine fraction constant is actually equal with a classical radius of the electron, Re. Physicists know about these concepts, to the Compton radius, or also called the reduced Compton wavelength, which is symbolized with this Greek lambda, with this dashed Greek lambda. And astonishing, without any fitting in my model, because this model is also I simulated it with Wolfram alpha to verify the known values, the properties of the electron, the angular momentum, its charge, its magnetic dipole moment, and so on. Yes, without blindfolded, I also found in my research that this diameter here of this straw is actually the classical radius of the electrons, which is 2.81 femtometers, 2.82, 81, 82 femtometers, and the whole charge radius, surprisingly, I also found blindfolded in my experiment that this must be the Compton radius of the electron, which is about 3.86, 10 to the minus 3, 13 meters. So it's a fraction of a picometer, actually, a fraction of a smaller than 1/10, of a picometer. Yes. So this is actually the fundamental points of my theory, some of the most fundamental points. But let's now go back and remember our initial question was why this angle? Yes, why is this angle? Why the electron, when you put it in an external field, straight flux lines, external field beam, it starts processing around its magnetic moment around with this specific angle, which is fixed. Why? So there must be an intrinsic reason for that. And yes, my theory says, as you see here, in the flux manifold of the charge of the electron, you have a specific, the flux lines are leaning, the flow of energy is leaning compared to the z-axis, to the plus z-axis, with a specific angle when passing through the equator. And my theory says exactly that. So this blue line represents the charge of flux, the vacuum flux of the charge of the electron. And here exactly at the equator, if you put a tangent line in one of these flux lines, it forms exactly this magic angle of 54.7 degrees to the z-axis, to the plus z-axis. And this is this resembles we can say a right threaded or left threaded screw, where we have the threads of the screw has a specific angle to along the z-axis of the screw, this mechanical screw. This is also the reason my theory suggests is why the electron has this angle, because it interferes, this skewed flux of the charge of the electron interferes with the straight flux lines of the external field, and always produces this precession angle of this fixed angle, the magic angle 54.7, which is intrinsic to the charge of the electron. So imagine like a pole dancer, a pole dancer, and he goes around, he processes around the pole, but we cannot control in quantum mechanics if the pole dancer faces, his face faces the ceiling or the floor down. So that's the problem again with quantum communication, quantum entangled communication, the non-communication theorem, because you cannot control the quantum spin of the electron to make it to always be, for example, precessing with a vector here, the intrinsic magnetic moment, because The magnetic moment vector always points from the south pole to the north pole, to the north magnetic pole. So this is black vector here is the intrinsic magnetic moment of the electron. Here is its north pole, and here down is the south magnetic pole. So if it's aligned with a magnetic field, it will have the same direction, this vector, with the vector of the external magnetic field. The magnetic field, also the external, has a south here, south pole here, and here up and now a north polarity. Whenever these two vectors align, then we say we have parallel alignment of the intrinsic magnetic moment of the electron with the external field. If it's not aligned and it's in the opposite direction, because it can have only two directions, the alignment, either parallel, either with a face down with a antiparallel, which we call then it's the electron is antiparallel aligned. So we cannot control this. We cannot control if the pole dancer is facing with its face up or with its face down, facing down to the floor. And that's why we cannot transfer any useful information. But what if, again, what if we could control, exploit actually characteristic of the charge manifold of the electron, we can exploit it, and then we can force maybe the electron to be always parallel to the external field, and then assign bit 1 to that, or anti-parallel and assign a bit 0 to 1 to this. So this is also an indirect, if I can do that, if I can control the spin, this also directly or indirectly, whatever you like, proves my theory of the intrinsic mechanics of the electron. This was published first, and you will see that in the references. It's the base model of my theory. It's called of the intrinsic mechanics of the electron and the charge of the electron. It's called a half-spin fiber manifold of the electron. So it's a fiber because it's a string manifold, which describes the charge of the electron in a physical level. So yes, so the hypothesis again here is that maybe if we could use form a kind of not straight flux lines field, magnetic external field, but a helical external field, which the helix of this field match exactly the helical charge of the electron. This charge of the charge manifold of the electron and the helix, the helical external magnetic field, have now the same form. They have the same embedded, the same magic angle. The helix of the external field also have a pitch angle, which matches the pitch angle of the helical flux of the charge of the electron. Maybe then we can, because you imagine like a screw going inside a screw hole, maybe then, and they both match, maybe then we can control the spin of the electron, this quantum spin, and dictate, force it to be spin up or spin down, to be aligned parallel or anti-parallel with the external field. So this hypothesis says here, maybe then a helical external magnetic field B spin up or spin down. Yes, because the helical field can, although it has a helical flux, it can still have a spin up or spin down, meaning it have a north pole up on its south pole down, or vice versa. So yes, with a spin up or spin down with the pitch angle set at the magic angle value and resembling the threads of a left-handed screw matching the charge flux manifold of the free electron. Yes, because my theory says that the electron has intrinsically, it is a left-handed. The flux is leaning always to the left compared to the z-axis. So maybe if we use a left-handed magic angle helical field, we could then deterministically control the spin of the electron. Let me briefly show you what I mean by it has intrinsically a left-handed chirality. Let me demonstrate this, please. Let's go back. Yes. Yes. Yes, here. We will compare briefly. So here you have the electron. Give a minute, please. So yes, Here you have the electron, and here it is without precession. And this is the charge manifold of the electron. Here it's magnetic moment. So if you put here your finger, the right hand fingers, and bend it to the sense here on the left picture of the spin down animation of the electron. If you follow the clockwise directions with your hand, your thumb spins down. So this is the spin down electron. And likewise, here in the right hand animation, if you follow with you bend your fingers to the direction of the spin of the electron, which is here in the anti-clockwise direction, you will see that the thumb will point up. So this now is the animation for the spin up electron. Yes? But you see here the charge of the electron or the flux lines compared to the magnetic moment are always leaning to the left. All the flux lines are leaning to the left. Opposite, contrary, in a positron, so the electron has a charge minus charge. It's minus E, the charge. And this is also the reason convection theory says that the spin vector here, in this case, which the spin vector I meant here points down, the magnetic moment vector is always opposite to the spin vector, because exactly it has a minus E charge to the electron. You have the spin vector here, in this case, in the left-hand animation. The spin vector is the angular momentum spin vector is spinning down, whereas its magnetic moment vector it's up. So always in the electron, because it's minus charge, it has the vectors or the spin vectors and the magnetic moment vectors are always in opposite directions. Opposite, in the contrary, this is a positron, which has, I remind you, a plus E charge, not a minus charge, a positive electron charge. And here, always a theory says, not my theory, conventional theories, and I agree as well, the spin vector is always in the same direction with the magnetic moment vector. So if you briefly here use your right hand rule, and here for the left animation, the left side animation, if you turn it, bend the fingers to the direction, to the anti-clockwise direction of the physical spin of the electron, you will see the thumb pointing up. So this is a spin up positron, and this is accordingly a spin down positron. And here we see the charge flux of the lines of the electron, of the positron, sorry, are leaning to the right, opposite to the picture we had for the electron, where the flux lines, the charge flux lines are leaning always to the left relative to the magnetic moment axis. Yes? So that's why my theory says that intrinsically the charge of the electron is left-handed and the charge of the positron is right-handed. It's always like that. This is fixed. This is an intrinsic feature of the electron, that it has a left-handed handiness or chirality, the electron. That is why now we have to use also to match this characteristic, and always the threads we use here, the helical field must be also this kind left-handed. The threads of the external B field, helical field, must also lean to the left and have this specific pitch angle of 54.7 degrees. So this slide here summarizes this, or what we said up to now, that when you put an electron in a straight homogeneous field, which is these two, the black flux lines here, the straight lines, then it will precess around its magnetic moment axis, around its these black lines, the external field lines, with this specific angle. Why? Because it has its charge has a built-in intrinsic angle of this 54.7 angle, and then this will give this precession here with this exact angle. But if we instead of this straight flux line field, if we could put the charge, the free electron, in a kind of helical field matching the flux here, both the flux of the external field matches the charge flux of the electron with this specific angle, then maybe we could control the electron, the quantum spin of the electron, and force it to align, or also maybe force it to not align, be anti-parallel with external magnetic field. But anyway, we could 100%, ideally 100% control the spin of the electron. So this helical fields actually is nothing we cannot make. Here we see a tokamak reactor, which is the reactor responsible for doing nuclear fusion. And in order to better confine this magenta field, which is the plasma, in order to better confine it, they actually use this kind of helical field technology. And this is here represented with the yellow arrows. But this angle here, this pitch angle, is very, very shallow. It's about 1, 2, at most 3 degrees. But now we're talking about an angle of the helical field 54.7 degrees. Yes. So we have to do the experiment. Probably the best experiment to verify our hypothesis, our theory that we can control the quantum spin of the electron, is the Stern-Gerlach experiment. And the Stern-Gerlach experiment needs, so we use a modified field. We don't use the classical inhomogeneous field of the Stern-Gerlach experiment. We replace that with our helical field of this specific magic angle of 54.7 degrees, and see the results. So the Stern-Gerlach experiment, the classical Stern-Gerlach, produced in the background screen, the detector screen behind, where the electrons are hitting, it always leaves this quantum spin, the quantization of spin in space in the electron, this characteristic ellipse pattern or UFO, so that you have here empty space where no electron had hit the screen, and this black here manifold pattern here, where all the electrons fall. And this is exactly the quantization of the spin, because if the phenomenon was classical, it would also fill in this region, this middle region. But exactly because the spin of the electron is quantized only in these two angles, spin up and spin down, and with this specific angle 54.7, you get always the magic angle above, and it's complementary in the minus z axis, plus z axis minus z axis. So if my hypothesis is correct, our hypothesis is correct, and we could control the spin of the electron, we will not see this pattern. We will just see half of the pattern, either the upper spin down or the spin up pattern, but not the whole pattern. This is what my theory predicts for if we do a modified experiment of Gerlach experiment, modified with the proposed specific helical magnetic field I proposed of magic angle 54.7 approximately. But now we have a problem here in my department, because our department is electronics engineering department, and unfortunately, presently we do not have a high vacuum apparatus, because Stern-Gerlach experiment demands a very high vacuum in order to perform this experiment. So we don't have this. So this experiment was out of the question. But we find the next best thing, which is this material. It's a powder actually of nanoparticles. A powder. It's DPPH. DPPH, we can say it's a macroscopic quantum spin emulator material. It emulates the quantum spin of particles, of fermions, and specifically, more likely, the spin of the electron. So what is this material? So we can use this material for our experiment without using it doesn't need any high vacuum. This is actually used also in electron paramagnetic resonance, EPR, as a calibration reference material, because this material has a G factor very close to that of an electron. So the electron is, if I remember correctly, is here 2.0023, and the TPPH material has 2.0036. So it can be used as a calibration material, a calibration reference material for this for electron paramagnetic resonance spectrography. So yes, and this is its molecular formula, and so one characteristic of this very rare material is that it has one unpaired electron per molecule. It's roughly about one unpaired electron every 41 atoms. So this actually resembles some kind of because it's an very loosely bonded one paired electron. It emulates a free electron essentially, and we can use that to do our experiment. It demands to have free electrons, so we can use the unpaired electrons of this material to emulate the actual quantum behavior of a free electron. It's specifically its quantum spin. So this material, another very important characteristic is exactly because the previous future, it is also paramagnetic. What means paramagnetic? Paramagnetic means actually something like aluminum, or aluminum we call it. In England, it's called aluminum, and Americans prefer to call it aluminum. So it's actually not magnetized. It's very, very, aluminum is not magnetized. But if you put it in an extremely strong magnetic field, it gets actually attracted. Yes, but usually paramagnetic materials, we refer to materials which are not magnetic. And why is that? Because the populations of unpaired electrons, remember the quantum spin, that we cannot control it. So maybe for example, 50.09% of the population aligns to external magnetic field, and 49.91% of the population does not align parallel by an external magnetic field applied, but is in the opposite direction, anti-parallel. But because there's a small difference in this kind of materials, just a very small fraction of 1% difference, this exactly gives the paramagnetic value of because if it was exactly 50-50, it would be not magnetic at all. This material actually we call diamagnetic, but because there's a small population, majority of the population, a small vote majority that is more than the other majority of the anti-parallel alignment, this gives exactly this paramagnetic characteristic of the material, that it can be magnetized, but it must be but an extremely large external magnetic field must be applied. So, and one very important parameter to measure this magnetization is the relative magnetic permeability of the material, because it's paramagnetic, very lightly magnetized, can be very lightly magnetized. It has a value of 1.0001, 3 zeros and 1. This is similar to what of aluminum has. Yes, and this always paramagnetic materials have this kind of value. It's 1 and then followed by 3 zeros and then a small value, a small digit 1, 2, 3, or so, something like that. In order to be magnetic, ferromagnetic, this value is much larger. So, for example, iron, which is magnetic, ferromagnetic, can have a value of 1,000, 2,000, and even ferrite material, ferrites, are also can have in the value of 400, 200, 2,000 magnetic permeability value, relative magnetic permeability. But yes, whatever is larger than 1, one digit, like 1.1, 1.2, 1.3, this is also considered as being a ferromagnetic material. Yes, so it has not been 1,000. A fraction larger than first digit, 1.1, 1.2, yes, it's also called ferromagnetic. And I say that because it is important for the presentation of the next slides. So we actually did the experiment, and we had also, I will present you the first preliminary results. So here we have, and sorry, this is the slide is not very clear. I will present from a bigger picture here, bigger picture. And yes, sorry. Yes. So this is how helical magic angle helical solenoid, and we calculated for a pitch angle, the whole length of the solenoid is 22.7 centimeters. And when we use a pitch angle, a pitch distance here of 2.27 centimeter, one train of the wire from the other, then this produces, mathematically calculated, this produces exactly a magic angle of 54.74. So if we use, if we wind here on the ferrite, this here is a ferrite core, yes, 1 centimeter ferrite diameter ferrite core. If we wind the wire around it with this angle, then this will produce the magic angle with this pitch distance here. And then, of course, this will also then translate it to helical magnetic field inside here, the ferrite core. That's what we want. And we needed for our experiment to know the exact value of the ferrite core, the magnetic permeability of the rod, which is different from the material of the ferrite. Ferrite are actually oxides of iron. This kind of materials are called ferrite. So it's some kind of oxide of iron. And this got pressed together, formed this rod. So we used, we measured the inductance of the whole here rod with a solenoid using a 1 kilohertz frequency. Of course, in our experiment, we used just DC current, but because we needed to calculate this magnetic permeability of the rod, we used AC to measure its inductance. And the inductance we have measured with an RLC bridge, very accurate, to be approximately 7 microhenry. So then we use this 7 microhenry and calculated the effective rod magnetic permeability of the ferrite, which was 154. So this rod strengthens up the magnetic field compared to an air solenoid without the core inside 154 times. That's the whole purpose of what this figure says. Yes. So then also we did a cavity inside, but I must say here that this rod is split. Yes, for the prediction says that for a current, DC current here of 675 milliamps, it will produce a 10 millitesla external magnetic field inside here the core. But this is for a normal coil, a normal one core. And what I mean by normally one core, I mean that the coils, the windings of the coil have not this pitch angle, this helical form, but each turn is parallel to the other. This is a normal wound coil. And for this coil, but with the same exactly inductance of our coil of 7 microhenry, this will give a 10 millitesla internal field with a 675 milliamp current here in the coil. Yes. So back to the cavity. The cavity is because the ferrite it's a two-part ferrite. It has two equal parts, left and right, and we put them in physical contact together, not glued, but with pressure, with an outside here envelopment. We pressurize them to be together, and we have drilled here a cavity, but not in both of the sides of the two parts of this ferrite core, but only on the left part. So it's actually split here in the center, and we drilled in a cavity of 5 millimeter in diameters and 5 millimeter in depth. Depth of the cavity. This cavity is then filled up with this TPPH material. And we measure with a Hall magnetometer the magnetic field for specific current values in physical contact with the ferrite. Secondly, inside the cavity without the cavity filled in, so it's a cavity filled with air. And thirdly, we measure the values with a cavity filled up to the rim with TPPH. So we have three sets of measurements, measuring directly the field inside the ferrite core, inside an air cavity, and inside the cavity filled with TPPH. And this then will allow us to do all the comparisons we need and calculations to confirm, to make conclusions of our experiment. So we continue now with the presentation. Yes. Yes. Sorry. The hypothesis. Okay. So this is actually a picture of an actual picture of the experiment. This is a whole magnetometer. This is this specific magic angle solenoid we have wound, and we use a 3D kind of guide, a 3D guide, this white stuff, to exactly wind the coil with this specific pitch angle of 54.7 degrees compared to the axis here of the electron. Yes. So in order to be accurate, we use a 3D printing here, this white stuff. We inserted the ferrite core inside, and this is the whole magnetometer. So the whole magnetometer, you cannot see the tip of the magnetometer, which is inside now the hole we drilled, the cavity. And as you also see here, a part of the cavity, this round cavity, we have also drilled a channel. So the sensor can pass in the whole magnetometer. So the whole magnetometer has this small PCB here, this plastic, and at the end of the tip here is the chip sensor. The chip sensor can face either this way or either the other way. So in here, if we turn the chip sensor to face the right hand of the ferrite, it is actually in physical contact with the ferrite, and we measure the field of the ferrite now inside the ferrite. But if we turn the probe here, so the chip sensor to face the left-hand side, then the sensor actually faces the cavity. And now we can measure the cavity either filled with air or filled with this powder, this TPPH quantum spin emulator material. So this is the whole setup we can see here. This is just a power supply, and yeah, the magnetometer, the special wound magic angle helical solenoid, the probe here, and this is just a current limiter resistor to current them. Do not blow up things, with the excessive current. So this is actually this cartoon says that if we wound counterclockwise, which means each turn leans to the left, as we start here from the beginning, which we need this characteristic. Remember, we have in our theory the charge flux of electrons is actually a left-threaded screw. So we need this left-handed manifold, and we use this type of winding, the counterclock winding of the coil. And then this will use conventional sense of the electric current, which says that the electric current flows from the positive voltage terminal to the negative. So this is a positive power supply terminal, and this is then connected to the to the negative power supply terminal. It's like a battery, no? Then when we use the conventional flow of current, we'll get the magnetic north pole of the solenoid here in the right hand, and the south magnetic pole in the left hand. And this is accordingly for a clockwise wounded coil using not counterclockwise direction of winding, but clockwise direction, the same as a clock. Then this will produce opposite magnetic field. Now the south magnetic pole will be on the right, and the north magnetic pole will be on the left. But we use this first case here with the counterclock winding of the coil. Yeah. So here in our picture, the north magnetic pole of the solenoid is here on the right hand, and here on the left hand is the south magnetic pole. And the whole magnetometer can also measure this. It can give polarity. So now here is the DPPH material. We bought this from Germany, and it cost us, without shipping expensive, 200 euros. 1 gram costed us 200 euros. Of course, we don't use the whole 1 gram. We use just 36 milligrams. This is actually the value we needed to fill up completely this cavity. We calculated that we need 36 milligrams to fill up the cavity. And yes, we used a scale here with 1 milligram resolution to measure the quantity we wanted of DPPH material. So now for the first time, I will present you the preliminary results of this experiment for confirming the control of the deterministic control of a quantum spin of the electrons, of the free electrons. So yes, so here, this dashed line is the predicted values, theory says, of a ferrite core, which is this kind of 154 relative magnetic permeability we have previously measured. What would be the field inside the ferrite core when various values of electric currents are flowing through the solenoid? So you have half, 1.5, 2 amps current, and the specific strength of the field inside the coil in milliteslas. So we see here, this is the line, the predicted, what the theory says, but always for a normal wound coil, which means that the turns of the coil are parallel with each other. They are not helical. But of course, with the same inductance we use of 7 microhenry. So both of the helical field of the helical coil with wound, with a predicted here of for the normal coil, both of the coils have the same, are calculated for the same inductance of 7 microhenry. So the result should be actually the same. It's not really difference. If they have the same inductance, the same should be identical, independent if the one has a helical wounding and the other has a normal parallel turns winding. So we see here a boost, already a boost. It's an average of 66.6% boost, which is very large. So the dashed line is the theoretical predicted, and this is the actually measured values. The ones we did with we turned here the probe so that the chip is in contact with the part of the ferrite which has no a hole drilled on it. So it measures actually the field inside the ferrite. Yes. So this was already a boost, but we cannot use this result because the ferrite is not a paramagnetic material. The core is ferrimagnetic and it has a quite large magnetic permeability value. But the next part is the important part, because now this pair of lines here is actually what we wanted to see. Here, the dotted lines is the values we measured in the air cavity, when the cavity was empty. So we turned the sensor to face now, the sensor of the probe of the whole magnetometer is facing now the cavity. Yes, so just skimming the cavity. But the cavity is not filled, it's filled with air. So actually we measure now the magnetic field on air. Yes? It's not the same as exactly as the magnetic field if the coil was totally empty and all air solenoid, because we have now, even if it's empty, the cavity is filled with air, 5 millimeter behind we have still ferrite material. So not exactly the same, but anyway, we want to measure what will be the values of the magnetic field when the cavity was empty. Well, not empty, because this experiment does not need a vacuum, filled with air. Yes? And the black line, this is important now, is when we fill the rim, up to the rim, this cavity, with DPPH powder. So this now is this things gets abnormal because theory says that these two lines should be actually tangent. They should touch it together. They should be together. Not this boost. We see here enormous boost. It's enormous boost of 52.3% in average of the values of the magnetic field measured with air and filled with TPPH. This should not exist because the TPPH is paramagnetic. It has no contribution, very small contribution, just fraction of a micro Tesla. Micro Tesla is 1/1,000,000th of a Tesla. So it should, these two lines compared with air, with or without the PPH, should be actually the same, should be tangent. So this is the first abnormal results, which suggest that yes, somehow this helical magnetic field forces more and more unpaired electrons of the TPPH material to align with the external field. That's why the magnetization contribution is increased, and therefore, because more and more of the population is not anymore 50.09% compared to 49.91%. Now it's getting more and more electrons aligning with external field. So it's not, for example, 55% aligned with external magnetic field, or 60 or 65. So this gives this magnetization boost. And actually, when we translate that to magnetization contribution of the material, the alignment is not just, the boost is not just 52.3%, but hold on, the alignment of the magnetization contribution is measured plus 32,000% in average, above, boost. I repeat, the magnetization contribution of the DPPH material, which should be just 0, is now measured 60, not exactly 0, but very, very small. You imagine, it's now measured plus 32,000% times percent in average. Boost, or more. It's enormous. This should not happen. So we can now see in this table, this is even more explanatory. So we have here what we measured when the cavity was empty on air, and when you say why are these strange values? So these values is for several values of current. So with this, for example, for half amp, for 1 amp, for 2 amps current, and then we measure the magnetic field with a magnetometer, with a whole magnetometer. And each row, each line here of these values corresponds to 5 runs of the experiment. So we did 5 runs for each of these values of the experiment, and then we average. So all these values represent the average value of 5 runs of each of 5 runs of the experiment, measuring these exact values. So we see here on air 2.5 millitesla. Millitesla is 1,000 of a Tesla. And then when we fill the cavity up to the rim with TPPH, we measured almost twice, 4.2. This should not happen. They should be both the same, actually, not twice the strength. So theory predicts that the contribution should be only of this 36 milligram of TPPH should be only 0.227 microtesla. 1 microtesla is a millionth of a Tesla. So the contribution is predicted to be 0.227, and we measured actually 1,700 microteslas. So theory predicts a fraction of 1 microtesla, and the boost was 1,700 microteslas, which is almost more, it's more than 7,000 times more than the actual prediction of the theory. It's a discrepancy of 7,000 more times. And this was for all the measurements here. For all the measurements, we have a 1,000-fold discrepancy compared to the predicted theoretical values. And then when we calculated from our measurements what this corresponds to a relative magnetic permeability, we found astonishing values of 1.4. Remember, the typical values measured for dBPH is actually 1.001, but we measure 1,000 times more increase of magnetic or relative magnetic permeability. We measure 1.4, 1.3. Yeah. So this is it's actually here you have 3 digits and it's full. It's almost it's 1,000-fold increase of the relative magnetic permeability of this material. So what we actually did, we transmuted now the material. That's the right word. Yes. What our results here suggest is that we have actually transmuted the paramagnetic material to a ferromagnetic. Because you remember, whatever is larger than 1, even in the first digit, 1.1, 1.2, it's not anymore called paramagnetic, it's called ferromagnetic. It's not, I mean, it's not ferromagnetic like iron, which has 1,000 magnetic permeability, or the ferrite material, the one used for the core, which is, we measured 154. But it's not, it cannot regard anymore, it's 1,000-fold increase in the magnetization property of material. It cannot regard anymore paramagnetic, it's now a ferromagnet. So we actually transmuted the material from being paramagnetic to ferromagnetic. And what does this mean? It means that it actually indirectly confirms our model and theory of the inherent mechanics and charge flux manifold of the electron, and that by using a helical field matching the charge flux manifold of the magic angle of the electron, we can then control the spin of the electron in a large percent, and even up to nearly 100%. And then, yes, one of the implications of our research will be that this opens up possibility for having digital binary information transfer between quantum spin entangled systems. So we can have potentially now we can control the information, this quantum spin. It's not anymore random, and we can assign it to bit 1 spin up and logic bit 0 to spin down. And yes, then we can have quantum entangled communicating systems. This is the base. So we can have instantaneous transmission of information, independent of distance. Because that's actually what entanglement says. It's a non-local effect. Or you can call it as a superluminal. Yes? So you can have actually superluminal communication. Yes. So these are the reference. This references covers all the results the last 5 years we did of the base model of the specific flux manifold of the electron. And this second here reference. This is the base model of the electron, and all the related research up to the today research. And but the today research has also preliminary results which are unpublished, and we hope we will publish this material the next semester of the summer semester of 2025. So yes, thank you guys for watching me, and be patient to have the patience to keep with me and see my presentation. But because before we go, just please two more slides. I present 2 more slides because it's very important. One of the most important observations of my research. So yes, a bonus. So remember that what my model says. It has the charge of an electron has actually 2 types of oscillation, theta per vacuum. So the theta per vacuum is a composite oscillation. It has the charge is revolving, and this is with the speed of light c. Yes, it's revolving along the z-axis, along the magnetic moment axis. And also, initially, my theory says that the whole manifold, the whole mass of the electron, actually also spins around the z-axis at c again. So I have initially assigned in my theory, and also later in my simulation of the model with Wolfram alpha, this value, the c speed of light, to these 2 oscillations. But then I came to a potentially big problem. because you see the Dirac G factor quantum mechanics is measured, quantum mechanics measures is at 2, the G factor. Because my theory is a classical theory, the G factor, I was actually expecting this, the G factor to come as 1. Because classical, that's the problem with all the scientists who try to explain classically or semi-classical the electron face the same problem. They come with a G factor of 1. But then the quantum physicists say, yeah, your model is wrong because we can actually measure in the lab this G factor 2. So you say 1, so your theory is kaput. It's not, something is wrong with your theory. So that's why also you heard that the spin of the electron has no classical explanation because it cannot classical theory says it should have be values of 1 and having therefore a 2 pi symmetry. But in the lab, we always measure this quantum spin having a G factor of 2 and a 4 pi symmetry. Yeah, but my results are getting even stranger because I found 1.15, not even 1. So or the reciprocal of what is of this is 1 over G factor of this 115 is 0.866. Please keep in mind this here value because it's very important for the next slide I will present. This is actually the key for understanding the whole quantum behavior of the electron, which can actually explain classically. And I will do that now in the next few moments. So please bear in mind with me because this is getting very interesting. So put your investigator hat, please. Yes. So this here, this is just I came from tennis and I'm sweating. Yes, and yeah. So so again, back to us. So why I found 115? I had a conversation a couple of years ago with one of my peers, Preston Jean. I will Preston Jean. You can find him, and he's very known atomic physicist and experimenter. He can find his work in the ResearchGate. Just search under the name Preston Jean. And this peer of mine and friend also suggested that maybe this kind of rotation here is not at c speed, because you again this actually presents the whole manifold is different. Here you have only a surface flow, but now there the whole manifold spins around in a vacuum space, in a Cartesian space. So then this may be because this is actually something like the mass, yeah. And the mass, you can say nothing massive can exceed the speed or be the speed of light c in the vacuum. Massive objects or particles must be always in subluminal speed and not at c. So now he suggested that he actually used similar models for his research, and he says that this speed is actually 0.866 times c. But I came in my experiment, in my simulation came also against this value. This reciprocal of 115 is 0.866. And this actually translates to the quantum angle of the electron, which is exactly 54. The angle is 54.74, the magic angle. But it's if you want to, the exact value of this 0.866 is square root of 3 divided by 2. Square root of 3 divided by 2 results to this magic angle and actually to this speed. It's square root of 3 divided by 2 is actually this 0.866 times the speed of light c. So and then when I put this value in my simulation, not c but 0. This value, but actually the value this value here. So now I set up the simulation with this parameter, not the c. I left this to c, of course, but here I put the value square root of 3 divided by 2 times c, which is approximately 0.866C. When I did that, then yes, you guessed correctly, the G factor of my simulation and theory came exactly 1. So now this is not 115. It came with this modification. It came exactly 1. That was what also the classical 2p symmetry model of the electron suggests, and also found by other researchers as well. But I was not satisfied because now we have the discrepancy between the classical model of the electron with the actually quantum model of the electron and measurements, which suggest a G Dirac factor of 2, not 1. Yes? And remember, my novel theory says that this actually ratio is the frequency ratio in hertz between this rotation over this rotation. So this here should spin with twice as this revolution here. But I find it to be the same. So the time it takes to have this full rotation, it takes to have this full rotation. So it's a 2 pi symmetry. But the quantum, what we measure in the lab, it's actually a 4 pi symmetry, 720 degrees, not 360 degrees. So what's going on here? But then I came with another coincidence. It's not coincidence, it's a fact. Sorry, not a coincidence. Actually, a speed of 0.86, if we assume that the electron actually spins physically with that kind of tangential speed at the equator of 0.866C, then the whole electron charge is subject of relativistic spin and specifically of time dilation. Because it's the speed now is subluminal, then the charge of the electron, if it's spinning at subluminal speed, and exactly this value here, then it's subject of relativistic time dilation. And when you put a calculation, this speed results at a Lorentz factor of exactly 2. So this square root of 3 divided by Tc, approximately 1.866C, if you do the calculation and calculate the Lorentz gamma factor, not G factor, the Greek gamma factor, it results to exactly 2, a Lorentz factor of 2, which means we have a time dilation of 2. And now comes the epiphany I had 2 years ago, because it's now the charge of the electron, its spin is time dilated times 2. The explanation, the electron mass, so I mean by electron means this 3D volume charge flux manifold of the electron. The electron mass, because it's physically spinning at speed square root of 3 divided by 2c, yeah, then this translates to a Lorentz factor of 2 and make it subject of relativistic time dilation times 2 in the lab frame. Thus, the 2 pi symmetry of the electron inside the particles frame is time dilated times 2 to 4 pi symmetry in the lab frame when measured. I explained what I'm saying. I'm not saying that this is wrong, that the 4 pi symmetry with measuring the lab with a neutron deformity experiments is wrong. No, it's actually 4 pi symmetry. But this, my theory says, is a quantum relativistic effect. Yes, similar to a Thomas precession relativistic effect. Inside the particle frames, the symmetry is actually the normal what we would expect from classical mechanics. It's the charge of the electron has a 2 pi symmetry. It means inside the particle frames, when we turn the 360 degrees the electron, it will return to the same phase. But we measure something different in the lab frame. We measure that we have to make 2 turns, 720 degrees, so the electron will measure at the same phase. But my theory says that this is a quantum relativistic effect. The 2 pi is time dated. The 2 pi exists inside the particles frame. It's time dilated times 2, thus from 2 pi to 4 pi, symmetry in the lab frame when measured. I think this is, if this can be verified, we have a total classical explanation of the quantum spin of the electron. And probably, maybe this means that also there are no two sets of physics, quantum physics and classical physics, and there are only physics we understand and physics we do not understand. Yes. So yes, guys, sorry for taking your time, and hopefully this was inspiring for some of you. And again, thank you very much for coping with me. And yes, so so yes, so yes, yes, that's I wanted to say to you, and have a nice rest of the summer. It's very hot here in Crete, in Greece, in the island of Crete, in the island of Greece, Crete. And yes, thank you very much, Emmanuel from Markoulakis from the Hellenic Mediterranean University. Bye bye.